So today is going to be a relative crash course in AI. So we're going to talk about, not necessarily in this order, but basically we're going to talk about AI UCF as a club. We're going to cover an overview of machine learning, so a very specific form of AI, and then a somewhat technical intro, but I'm focusing more on getting everyone sort of acquainted with the variety of machine learning approaches, as opposed to let's zero in on one specific thing, and I'll clarify why in a minute. And then we're also going to talk about career prospects. So like, what would you expect to do with a career related to AI? And so like it says, the appendix is not currently full as I would like, is not currently entirely full, but it will be full by tonight with other resources. So basically like pointing you, so if you wanted to go learn about one of the models that we use today, I'll have more resources there than just the descriptions that I've given on Kaggle. Also, if it's feasible, could everyone head over to the sign up link there? That's for tracking attendance for AI UCF. Yeah, so I'll give about a minute for that. All right, so hopefully everyone has been able to fill that out. If you haven't, then just like drop something in the chat so that I know not to move past yet. Okay, sweet. So yeah, so the disclaimers and clarifications that I was getting at. Today's going to be relatively conceptual. The workshop is mostly going to be a walkthrough, and that's just based on time constraints, as well as sort of the expectation of knowledge that I kind of set based on the form responses that I got. The expectation is basically no one's really ever like been exposed to machine learning in any way. Or like if they have, it's mostly been like through like pop sci articles, as opposed to like having a technical understanding. And there doesn't seem to be a whole lot of familiarity with Python. And because we only have about 2 hours, it's at least more straightforward in terms of being able to cover ground. I see it as more straightforward for us to do this, and then I'll just annotate the living hell out of everything, or have already done that, so that you can go and do this on your own time as well. And that's mostly leading to the second point of, if you want to get into AI, it's going to take a lot more than even 10 hours. And that's mostly why I've framed the deck as it is, which is more of a launching point for you, and to basically figure out like, where do you want to go? What are the kinds of machine learning problems that you're interested in? And what are the kinds of algorithms that you're interested in, and the like. And then one sort of clarification is that depending on what it is that you're interested in, if it's explicitly like the model building side of machine learning, which you'll probably figure out over time, the model side, like the model building side, normally accounts for less than like 15% of what you do in your day-to-day in industry, as well as in academia post a PhD. So that's something to just like consider, is if that's the sort of stuff that really interests you, then there might be like a ceiling in terms of advancement, because you want to stick to the things that you're interested in, or because you might want to stick to the things you're interested in. So yeah, so On to the next thing. So why should you trust me? Essentially, while I was at UCF, I was a researcher in the NLP group and the Center for Research in Computer Vision, run by Dr. Shaw. The NLP group's run by Dr. Fei Liu. She's dope. I was a contractor for Udacity, where I mentored north of 300 students across 10 different nano degrees. So their nano degrees are basically 0 to somewhat hero in machine learning, artificial intelligence, deep reinforcement learning, robotics, stuff like that. I also founded at UCF. I designed the majority of CORE's curriculum as it is today. And I co-created discussions and projects, and I'm also helping with the redesign of CORE to cover an even wider breadth of topics than are currently covered. So then post UCF, so I graduated in December 2019 with computer science, math, cog sci, and robotics. And I'm now a researcher at Harvard and MIT at the intersection of AI and cognitive science. Basically, that just means that I use tools from computer science and AI to better understand human cognition. And I use the findings from cognitive science to hopefully build better algorithms for AI and machine learning. And then on occasion, I'll also do consulting in AI and data science as freelance. The point of all of that is, I think I know what I'm talking about. So yeah. So kind of what we're looking at doing today. So plugging AI at UCF really quickly, career prospects, clarifying nomenclature, and then actually diving into the workshop. So shameless plug, basically talking about AI at UCF. For those of you that are unfamiliar, so that Discord link down in the bottom right, that's for AI at UCF. So if you want to join that, feel free. And then, so the mission of AI at UCF is basically to foster a hotspot for the next generation of intelligence researchers and engineers, as you can read. And so what that's really getting at is modern day machine learning and AI related algorithms they don't seem to actually practice intelligence. They seem to be really good at pattern recognition, and they happen to beat humans on very specific tasks. But the moment you try and take that same model, that same algorithm, and transfer it to something new, you either have to restart it from scratch in terms of getting it to learn, or it's just going to fail abysmally. So it doesn't necessarily generate this flexibility that we see in humans and even other animals on the planet as well. And so there's this broader push now from particularly cognitive science to try and build computational models of these ideas. And there's also just a broader push to try and move AI and machine learning away from what we've been doing, which is basically how high can you get on the leaderboard? Just because you can advance on the leaderboard doesn't mean your algorithms are actually learning the concepts that you're trying to get them to learn. They're oftentimes just learning the patterns that exist and really being constrained by the patterns and not having the flexibility to basically take a concept and transfer it to something else the way that a human can. So I know that that's vague and kind of hand wavy. If you want, afterwards, we can talk a little bit more about that because it's actually some pretty cool stuff. But yeah, so really quickly, in case you're unfamiliar with AI at UCF, so groups are how they tailor content. And so there's GBMs, which are explicitly focused on sort of lay people where you're not super familiar, or you have you think AI is cool, but you're not sure if you want to do it, and so on. And so those are pretty interesting. I definitely recommend going to those if you haven't. Core currently isn't being taught this semester, but we are pointing people to older materials that we've recorded. And then we'll be doing about the same in spring, which is basically trying to get you from knowing approximately nothing about machine learning and AI to a point where you could actually go up to any lab and on campus and say hey, I want to do research in your lab and I want to do it on this particular topic. And they'll normally take the credential or the projects that you've done and the things that you've learned in core, and they'll use that as, oh, so clearly you have at least an idea of what you're doing, to kind of put you in a better spot than where you might have been based on what we were saying on Monday, for those that went to the research panel, which was the assumption that professors don't really assume that you know anything. But anytime that they have a student that comes in and it's oh, this student might actually know something, that already puts you in a better spot for them to be more willing to take you on. Yeah, and then so there's discussions, which is a paper reading group. and it's targeted at like how can you learn, like can you learn to break down a research paper and to really not only understand it but also, yeah, so not only to understand it but also like efficiently read it so that you're not basically getting stuck on, yeah, so that you're not getting stuck while you're trying to read papers, because reading papers can be kind of a pain in the ass realistically. So part of discussions is trying to give you the toolkit to actually do that in a more efficient way, as well as to do that in an environment where it's not just you on like this lone journey reading a paper. And then projects is a team-based group where they form teams to build AI projects. I think one of the people here was actually talking about one of the projects in that group. So yeah. Does anyone have any questions in terms of AI at UCF or anything like that? Okay, cool. So career prospects. So what kinds of work can you do with data science, AI, machine learning, and the like? So something to bear in mind, I put can do in quotes because I'm not trying to be like super restrictive with what I say, but there are like, these are the 4 things that have stuck out to me while I was in undergrad, and from people that I've talked to, what also stuck out to them. So point is that there are arguably other things that you could do in your undergrad relating to machine learning, AI, and data science. But you can do research, and then you can probably do internships as well. In terms of research at UCF, there's a lot of computational work going on in computer vision and natural language summarization. There's a little bit of work going on in evolutionary computation, which is really cool. And so those are all things that we can talk about in more detail later, like so after the workshop and everything. But also like kind of acknowledging what was said on Monday of how just because you're doing computer science doesn't mean you have to stick to the CS department. You can also go to like biology labs or even chemistry and physics labs, and they're using machine learning. And so if you're looking to use machine learning and to get better at machine learning, and let's say you care about exoplanets, you can probably go do research in a physics lab, because there's a lot of exoplanet research going on at UCF. And then another thing is during your summers, you should definitely shoot for doing REUs, which typically is research at other universities. The main rationale for that is in preparation for grad school, you need 3 letters of rec. If you spend at least 2 of your summers doing REUs, you've basically got your 3 letters of rec for grad school. And there's the upshot, which is that not all of your letters came from the same place. When you have 3 letters from different places, that tends to look better on your application than having them all from UCF, for instance. So yeah. So in terms of internships, so when I say GAFA, I mean Big 4, Google, Amazon, Facebook, Apple. So a lot of this is taken mostly from Facebook because they seem to be the most progressive about getting like undergrads into data science and the like. But data engineering is normally what you'd have access to as an undergrad. And as an undergrad without being published in like a top tier conference or journal. And so that normally focuses on SQL and software engineering in some sort of marriage. At other places, I think that there was one coordinator in AI at UCF that did an internship at Microsoft, and he was doing almost entirely data engineer. Like I think he did data engineering at like the regular split that you'd expect. So 85% data engineering, 15% actual like modeling. But per his words, the way that he got that slot was through an insane amount of networking. And so that's just one thing to be aware of, is that like you are probably gonna have to network your way into a lot of these slots, because a lot of these slots they normally advertise for them and the like at really top tier schools, and the same thing applies for the research positions. So like the ML and AI side. They normally take you even if you don't have a publication, if you go to the likes of MIT and whatnot. Whereas for UCF, if you want to do that, they basically demand that you have this publication. And getting into those journals and conferences is exceptionally hard. And that's not meant as like to dissuade you, but rather it's meant to just like illustrate, hey, if you have these goals, it's going to take a lot of effort on your end. And it's doable, but it's also something that like there will probably come a time where you have to persevere through it. So yeah, it's not necessarily the like, yeah. So something else that's worth noting, if memory serves, Florida requires summer credits. So for those that might be concerned about like going and working, like doing 3 internships over the span of 4 years, and then you fail that requirement. From what I recall, and take this with like a salt mine, because I had this conversation, I think like 3 years ago. As far as I recall, there might, Kim Small, who's the assistant like director of advising or something, it seems as though there might be a way to sidestep that requirement so long as you have internship experience to compensate for it. I would definitely talk to her about that though. But if you can do that, then I'd say more power to you. It's definitely something that's worth doing, simply because the more summers you can spend doing things like this at other places, not only the more exposure you get because you're not sticking with UCF and what UCF does research on, because institutions have their specializations for research. So you're very likely to encounter something that you wouldn't have encountered otherwise. So yeah, and then what you can do sort of postgrad. So you could get a master's degree, or you could get a PhD, or you could do a postdoc, but the postdoc's going to require a PhD. And so a master's degree, like that's what most people tend towards as opposed to a PhD. It's debatable as to whether or not you should pick one over the other. If you're trying to get a company to pay for it, they're more likely to pay for a master's degree than a PhD. But with a PhD, what you're trying to do is you're trying to refine your skills as a researcher and develop some kind of research agenda. So all of that means is like, I find this set of questions fascinating, and because I find this set of questions fascinating, this is what I'm going to pursue for the next, I don't know, 10 to 40 years, depending on how hard the questions are. And so some might call that an unhealthy obsession. But yeah, point is that you would try and actually work towards those goals over a long period of time. And so a PhD is going to teach you that, whereas a master's degree won't necessarily teach you that. And part of that is just a time requirement. A master's degree will typically take you 2 to 4 years, depending on how you do it. A PhD will take you typically at minimum 4 years and up to 8. And they also have like very different bars of requirement. A PhD, you have to present something novel and unique. A master's degree, you reproduce someone's dissertation and then make some tweaks, and you got your master's thesis. So a master's degree is definitely like a lower bar to hit, but it's definitely something that would be useful if you're trying to do data science and data engineering. And potentially moving into research scientist. I haven't seen as many people that land research scientist slots with a master's degree. It's normally a PhD requirement. And so there's software engineering. So in terms of industry, there's software engineering, which I think everyone's familiar with. And as far as I've gathered, this typically has a pretty indirect route to data science. And if you do manage to land in data science in some way as a software engineer, you were probably working in industry for north of 10 years from what I've seen. And you may have also gotten a master's degree before they transition you into something like data science analytics. So data engineering is going to be building the data pipelines and the transformations that you do on the data. So that can entail things like if you receive a bunch of text data, then you're going out and you're parsing it in a special way that the models need, or something like that. And so this, depending on the kind of person you are, that could be absolutely fascinating. For others, it might be dull, but it's definitely a position that exists. This is something that typically only exists at medium to larger size companies. Whereas with like startups, everyone's a data scientist. And the data scientist just handles everything. And so that's something to also be aware of, is like, if you want to be able to do like the full stack, let's say, then you probably want to go work at a startup. So data science analytics is typically focused on like finding trends in data and developing the statistics over that data. And so that doesn't necessarily get at this idea of model building. You're doing more of just like statistics and analysis, like the name says. And so if that's stuff that tickles your fancy, then have at it. And as far as I recall, this guy who's in the 2 YouTube videos that I've linked here, he had a bachelor's degree and he was doing data science analytics. Now, something to bear in mind is he went to UToronto. UToronto in Canada is equivalent to like Stanford in the US. So he went to a relatively top tier school, and sadly, like pedigree matters. And so it could be that like he lucked out because he went to U Toronto, or it could be that just like Facebook, which I believe was the company that had employed him, was willing to take on a bachelor's student, but I'm not in, or someone with only a bachelor's degree. So you can obviously shoot for that. I'm not sure like where to kind of help you set your expectations in terms of, are you likely to get it? Are you likely not? But yeah. And then there's research scientist, which is like, if you're really more about building models and exploring essentially like the frontiers of how do you solve really hard problems with using machine learning, but in industry, a research scientist almost always requires a PhD. I know a few people who have lucked out and been able to do it with a master's degree, but they were only able to do it because they spent a summer doing a research internship as they were a PhD student. They spent a summer doing a research internship at the like at that company. So in this particular case, they spent a summer at Amazon. But they were doing their PhD while doing the internship. And then they decided to drop out, and Amazon gave them a return offer because of what they did. So like there are ways around it. And that's also why I put can do in quotes, because there are always ways around these things, at least for industry. For academia, there's none, sadly. But just another thing to kind of point out as a footnote, just because you get a master's or a PhD doesn't inherently shut your doors to industry. In fact, industry tends to want to poach masters and PhDs from academia. So odds are you're probably going to be perfectly fine if you go down the route of PhD or master's. So somebody asked, how do you do research at another university over the summer? That's something that I will answer right at the very end, because I have a bunch of slides for that, which I've basically put in the appendix. And so, yeah, so I'll get to that in a minute, or sorry, I'll get to that in like an hour and a half. Yeah, so that's pretty much all that I had in terms of like undergrad, postgrad, career-wise, without just like devolving into like career service. No, without devolving into something like a career services presentation. So does anyone have questions about these sorts of things or anything like that, or no? All right, sweet. So then actually talking about machine learning and AI and everything else. So something to bear in mind is, just due to time constraints, I'm not going to be as detailed as I could be, but part of that also ties in with the idea that I'm trying to present you with a breadth of information as opposed to with lots of depth. I'm leaving a lot of the depth up to you to do. And you can always, like I think I've said, and if I haven't, then I'll say it. You can always ask questions in the AI at UCF Discord. There are plenty of people who will answer. I'm one of them. And so, yeah, if you ever have like difficulty with a concept or anything like that, definitely feel free to ping anyone there. Yeah, so kind of starting out is just like a really high level. So like, what is this idea of artificial intelligence? And so potentially like you may have definitions that are shaped by like what you've read like on the news, or what you've read on blog posts or anything like that. But at least based on AIMA, which is Artificial Intelligence, a Modern Approach, which is basically the AI Bible for teaching, they go ahead and they define it as the study of agents that receive percepts from an environment and perform actions. Now, that's a really nebulous definition. And so all of that's really trying to get at is, it's something that interacts with the world, and as it interacts with the world, it acts intelligently, and in the way it acts intelligently, you can observe that through the actions it performs. So in the case of like a human, where you're interacting with the world, when you're taking an exam, for instance, the percepts in your environment are going to be like the question you're reading on your exam. And then the actions you're going to take are the solutions that you write down as part of answering your exam. And so that sort of idea is how they're defining artificial intelligence, is an agent. So this is basically just like an artificial entity. So that could be a robot, it could be like an avatar in a game or something like that, which is able to do which is able to perform these type of behaviors. Is that relatively clear so far? If it's not, I'll take some time to like further clarify it. Okay, so you have this like giant cloud of AI, which has all kinds of methods in it. But then within AI, you have this smaller region, which is machine learning. And so the reason I'm bringing this up is because for some reason, there's been this tendency to conflate AI and machine learning as either the same thing or two separate things. And they're not. Machine learning is a subset of AI. AI is a much bigger field. And what's interesting about it is that there are a lot of things that we call like object-oriented programming that initially fell under the umbrella of AI. And there are a lot of things that we've tried to build in computer science theory and just computer science in general that have typically fallen under the umbrella of AI until they become so well developed that they could be their own entity. As just like, here's this concept in computer science. If that if that makes sense. If it doesn't make sense, then please feel free to stop me. So within machine learning, you have like all kinds of things. And so that's what we're going to focus on today, which is, so you have things like random forests, you have supervised learning, you have naive Bayes, and that's just some of the like infinite things that exist in machine learning in terms of algorithmic approaches. And then there's this giant, like, so the giant green ball is deep learning. And so deep learning has kind of like taken the world by storm since 2012. And so it's what powers self-driving cars, it's what powers Google Translate, it's what powers Siri, it's what powers Google Assistant, etc. And deep learning is trying to use what are called neural networks, which are a gross approximation of the brain. It doesn't get anywhere near like the capacity of an actual neuron, but to say that they're loosely inspired is fine by the brain. And so, but the point is they have this massive capacity to actually represent functions. And so I'll get into that in a second. And so deep learning in particular is something that if you were to do research at UCF, especially, a lot of the labs that you'd be doing research in are going to end up using deep learning. Computer vision is basically just like become one with deep learning. And then natural language processing, which is the stuff that Dr. Liu does, has basically done the same. And so that's probably something to note down is like, I should learn deep learning. I'm not going to be able to cover it today just because of time, but I am going to do my best to like leave resources for you to go start learning about these ideas. So now let's talk about like that blue circle of machine learning. And so machine learning effectively, like you can think of it as a framework that allows you to curb the explicit like rule function based programming that you normally would do, like in CS1 and CS2, etc., where you're writing control flow to be able to say like, oh, if the program's in this state, do this thing. If the program's in that state, do this other thing. And you're writing functions to do all of this. Instead, what machine learning tries to do is it tries to learn how to do all of that by basically just like rendering what you could think of as just like, it's a polynomial. So like x to the fourth plus 12x minus 72. So obviously something more complicated than that, but that function is supposed to be able to represent most of what you're trying to do by writing all of this code by hand. And so what that's getting at is this idea called function approximation. So function approximation is essentially looking at, if you have like a bunch of points that are dotted around as if it looks like x squared, and you start from some random initial state, there's a way to actually optimize the function that you're using to generate this line to the point where it'll eventually converge onto, I think that's a parabola. I hope you can see that as a parabola, where it looks like x squared. And so, yeah, so that's all that machine learning really boils down to, but that actually gets really hard when you start looking at things like object recognition and being able to identify objects, being able to identify like key words that matter between sentences and like ideas and concepts and things like that. So basically when you scale it up to the real world, it gets really hard, which is why it's an active research field. So yeah, another thing that's just kind of like a point to note is that your algorithmic choices in machine learning matter a lot less than the data that you have access to. As Pedro Domingos, who's one of the thought leaders in machine learning has said multiple times, but in particular in this paper that I'm citing, more data beats a clever algorithm. And that's really what machine learning is. Machine learning is probably the most data hungry thing I've ever seen. You can chew through millions of examples and the machine will barely be able to understand something conceptually. And so that might be like a really fine and like nuanced line that I'm drawing, but the point that I'm trying to get at is it takes a lot of data for these algorithms to learn anything. And even the thing that they learn is very fragile. And so also like sort of another footnote is this idea that the training data that you have will bias your prediction results. And so what that means is that you can't expect a machine learning model to inherently like de-bias your data. So what that means by de-bias is, let's say that you have, so if we take like a recent scandal of machine learning, so we take like the Twitter or the idea with Twitter where you had, I think it was, what's his name? So you had Obama, some white block, and then you had Mitch McConnell. And you were looking at like, where does it rank? Like, where does Twitter crop that image? And so it ended up cropping either the white section or Mitch McConnell into view more often than it cropped Obama. And so part of the problem there, and so like, yes, like that's obviously a problem, but what I'm getting at is part of the problem with a lot of the reactions to that is a failure to understand like how these models work. These models are matching pixels and they're matching patterns. And so when your data, which it was trained on, was probably highly skewed towards Caucasian men or Caucasian people, when the model will reflect that bias is what I'm really trying to get at. And so it's the sort of thing where it's an expected output, but you may not see it until it's in practice. And there's a lot of research that actually goes on behind the scenes, not only probably at Twitter, but I know that there are other research labs that actually deal with this, which is basically looking at AI safety. So how do we build machine learning models that are actually able to go about the world and take the bias that we have in our world and extract a lot of that and basically remove a lot of that so that they can not only perform well, but they can perform in as unbiased a way as we can find. And so if that's something that's really interesting to you, like AI safety and the like, then there are a bunch of labs that do that. And that's an active area that like you could get a PhD in, and it's pretty cool. So yeah, so some uses of machine learning essentially boil down to, at least the ones that I know of fairly well, computer vision, natural language processing, recommendation systems. So think Netflix or Amazon. As well as like field-wise, there's a lot of machine learning that goes into robotics. There's a lot of machine learning that goes into cognitive science, especially this bit of trying to reverse engineer the mind, neuroscience with trying to reverse engineer the brain. And also, like the footnote says, there's a lot more to it. There are a lot more uses of machine learning than just what I have here. And so, yeah, so basically, as long as you have data, you can probably do something with machine learning. The upshot of doing something like research in your undergrad, you're going to be given the data. It's very rare that you're not. So yeah, and so you can the whole like summary of this slide is you can use it for literally anything. So yeah, so then some flavors of machine learning. There are 3 sort of guiding flavors, but you can definitely like add more. If you wanted to, or like if you were able to formalize that, which would also be pretty cool in and of itself. So there's one flavor called supervised learning, which is effectively the same thing as learning from flashcards. So the idea with that is, let's say on your flashcard, on one side you have the word, on the other side you have so on the other side you have a definition. And so on the side that has a definition, you feed that into your machine learning model, and then it maps out, or you feed that into like your brain, and then you're supposed to be able to map it to the right word that it's supposed to have. And in you learning how to make that mapping, that's the goal of supervised learning, which is to learn how to take this input that you have, so the definition, and map it to the label. And sometimes you can also get the reverse for free, depending on the models that you use. But the reverse would obviously be you have the word and now you can regurgitate the actual definition. So this is the most common and accessible form of machine learning. It's also the one that we're going to use today. And one of the main downfalls of supervised learning is that it tends to struggle with generalizing. So if you think back to like somewhere between like third and fifth grade, when you were doing flashcards, learning vocabulary, uh, odds are if you didn't understand, like especially if you didn't like learn the roots of words, you had to memorize every single definition that you were given, and sometimes that would be pretty overwhelming. And so when you were asked to potentially use synonyms of those words, that may not have worked out all that well. Whereas if you were to learn the actual roots of the words, so for instance, let's say that you have a decent understanding of Latin, magical third or fourth grader that you have a decent understanding of Latin. That odds are that will probably help you quite a bit when you're dealing with languages like French or Portuguese. And so the point is that because you can look at the roots like that, you can use the roots to determine what those actual words that you're looking at end up meaning. What? Oh. And so, yeah, so with unsupervised learning, which is another form, nope. That's typically implemented with clustering. The goal is essentially to learn from unlabeled data. So the idea with clustering is basically you have a bunch of points and you're trying to categorize them along some metric of some kind. So let's say that like you have, I had an example prepped and it's gone. Okay, so unsupervised learning is basically looking at clustering. Clustering is supposed to be this idea where you have these points and you're essentially just trying to find common features between these points that group them together in some way. So one of the main goals is, like it says, to learn from unlabeled data. And it's a relatively understudied area of machine learning. Part of that is just because like trying to learn from unlabeled data is a really hard thing to do, because in part, like you don't have a feedback signal. And so that's something that's really important for getting machines to learn on their own, is to give them some way of not only understanding the feedback that they get, but also like getting the right feedback. And so when you're dealing with unsupervised, it's kind of like pick your own feedback signal, and that can be pretty disastrous. I can talk about that in greater detail later, but yeah. And then the last flavor is reinforcement learning. And so this is largely inspired by human learning. And a lot of that is sort of an attempt to mimic the fact that we learn about the world by experiencing the world. So for instance, when presumably you were somewhere between 2 and 4, you probably stuck your finger in an outlet and learned the very hard way, like why you shouldn't do that. And so what you got is you got a feedback signal saying, no, don't do that. And the feedback signal that you got ideally taught you a lesson. And so another like potentially easier to understand example is, let's say that you're playing a game of chess. When you play a game of chess, let's say that it takes you like 75 moves to get to the end of the game. So if it takes you 75 moves and you end up losing, your feedback is that you lost the game, but it's very possible that you actually lost the game on the 25th move in. And so the point is that you were only told you lost the game. And because that's all that you were told, it's up to you to adjust your way of play, hopefully in some manner that actually allows you to sidestep whatever you did on that 25th step, so that you don't lose the game in the future. And so and so point is that ultimately, like, it makes it harder to actually learn about the world, or rather it makes it harder to learn, but it mimics human learning much more effectively than supervised learning does. Because like I don't go about the world just like learning everything that I do from flashcards. Hopefully not everyone does that either. And realistically they don't, because if you show like a 3-year-old dog, it can identify a dog and delineate dog from not dog for practically the rest of its life. And so something that's pretty interesting with reinforcement learning is that you have to build your own simulations. So if you're interested in doing stuff with simulations, or you're interested in doing stuff with video games, reinforcement learning uses those as test beds, because you have to build artificial environments for these models to actually go and explore. So it's possible that maybe that will be a way for you to merge two things that you enjoy. I don't know. And so the goal is to learn this policy, which it's a heuristic, all that means in like non-lingo terms is basically think of it as it's your gut intuition or your intuition, where over time your intuition probably changes about certain situations, but you still potentially trust your intuition. And so that's what your policy is. That's what the policy is. It's just more like well-defined in terms of computation. And so they develop, this policy as they learn. And the whole idea of the policy is that they can analyze what state of the world that they're in and use the policy to determine what the next action or next series of actions are. But also like kind of what I was getting at earlier, where reinforcement learning is often where like, or I was hinting at it, of how reinforcement learning is actually sample inefficient in most cases. And so the sample inefficiency, what like a straightforward example of that is like, let's say you're back as a kid again and you stick your finger in an outlet and you learn like that's not good, but then you start exploring other pieces of like the house or whatever. And then suddenly, like as you've been learning, somehow you actually unlearn the portion of the policy, or you like silence the portion of the policy that was like, don't stick your finger in the outlet. So then you do it again. And then you presumably learn, but then this process repeats to some degree until eventually you get to a point where you've learned everything and you've also learned don't stick, or rather you have a policy that says like, don't stick your finger in an outlet. But the idea is repeatedly making the same mistake or making the same erroneous, or like, yeah, essentially executing the same erroneous behavior. That's part of what sample inefficiency is kind of illustrated as, is like humans typically learn from one or two mistakes, depending on what the mistake is. They oftentimes learn from one, whereas reinforcement learning models normally need multiple mistakes that are of the same variety or exactly the same to be able to learn anything out of it. So yeah, and kind of like the footnote says, odds are there are probably more of these umbrellas, but these have been the umbrellas for the last like 30 or 40 years, I think. And they've generally been broad enough, but who knows? Maybe there's a new one somewhere. So yeah. So like I said, we're going to focus on supervised learning. So supervised learning is essentially characterized as you have some input data or some input and labels. So the inputs could be like that definition that I was talking about, and then the labels would be the word that you're mapping that definition to. And so you'll feed that into your model, which in this case is an orange circle as opposed to a black box. That's normally how it's referred to. But the idea is you feed this into this model and it does some magic, and then it spits out a prediction. And so that prediction that it spits out is normally characterized as classification or regression. So to actually talk about classification and regression, let's head over here. So the idea with regression is that you're going to end up spitting out a real value. You're going to be spitting out a number. And that could be spitting out the predicted price for a stock tomorrow or in 5 minutes, or the predicted price for like a temperature, the predicted temperature for tomorrow. And so you could be doing things like that, or you could be doing potentially predicting the grades that someone the grades that someone is likely to receive. Whereas a classification, you end up with, so with classification, you end up with, with classification, you're trying to basically categorize something into a variety of bins. So in this case, you're categorizing into one single bin, but there's also the possibility where you're actually trying to categorize a single data point or a single input into multiple bins. And so, so main delineation between regression and classification is that regression maps to some real value, which can be whatever set of units you want it to be, whereas classification tends to map to classes or bins. Multi-class assigns to exactly one label. Multi-label assigns to one or more labels. I don't know why they're named like that, but that's how they're named. So I'm sorry if that causes confusion. So what we're going to do is we're going to talk about here's some prominent algorithms that you should definitely look into. And so these are kind of ranked in some way in terms of increasing complexity, and also to some degree increasing like representation power. and like prowess when you're when you're handing it data. But yeah, so the ones that we're going to focus on, so I actually highlighted deep learning for some reason, but we're not going to do deep learning. We're going to do logistic regression, random forest, naive Bayes, k-nearest neighbors, gradient boosting, and decision trees. So that's for the workshop. And so these links are actually to other slides. I need to properly fill out the slides. But that's what I was getting at of it's going to be filled with like links for you to go look at and other sources that I've vetted either over time or found recently and mostly vetted in terms of understanding. So yeah, so that's pretty much it in terms of the conceptual overview. What I was trying to do was give you the conceptual understanding of how supervised learning works. And we're gonna like over time, you'll eventually like build the actual pipeline for that. But rather than trying to like lay the entire pipeline onto you, because that'll take more than 2 hours, I was trying to just focus on a conceptual understanding. So I want to make sure that everyone has, or that most of you have some degree of conceptual understanding. And it sort of feels like it all makes sense. Another thing that I want to also do is see if we can take a break, considering we've been going for 50 minutes. And we probably need like a 5-minute break just so everyone's not fried going into the workshop. Does anyone have any questions?
You have some questions in the chat, by the way.
Okay. Oh, so just to be clear, we can do the break like now until 6. Sorry, I thought I had made that a little clearer. So yeah, we'll pick back up at 6. So that's in like 3 minutes or so. Oh, okay. So one of the questions was, yeah, so one of the questions from, I believe your name's pronounced Keone. If it's not, let me know. But I'm gonna, so I actually, that's part of what I'm doing right now, is making that public. There's a link in the slide deck. Oh, I should have sent you all the link for the slide deck. Okay, so I'm going to make sure that the slide deck's visible. Okay, so I've sent the link for the slide deck in the chat. I will, I'll make sure that Chloe has it, or whoever it is that's editing the website. I'll make sure that they have it so that they can link it. So that's the link for the slide deck. Within it, there's going to be a link pointing you to the Kaggle kernel. So for those of you that aren't already signed up on Kaggle, please go ahead and do so now, so that by the time we start back up, everything should be good. And then for Rajiv, so a recommendation. So when you're asking about texts, are you referring to textbooks or are you referring to something beyond that? I think you should be able to just unmute yourself if it's easier.
Yeah, I was talking about textbooks primarily.
Yeah, so that one textbook that I was talking about, AIMA, Artificial Intelligence: A Modern Approach, is one that's definitely good. There are ways to avoid shelling out all of the money for it. If you want to know of those ways, then you can tell me later and not on Zoom, since this is recorded. But yeah, so there's that. There's another one which is called deep learning. So here. Where is it? Elites. Yeah, this.
Okay.
So it's called deeplearningbook.org. Yeah, but I'll also be putting all of these in the slide deck. So that's part of the reason for keep the link for the slide deck.
Okay.
Yeah, all of those are going to be linked. You can also definitely go to core. We don't cover absolutely everything, but we've been in the process of moving towards covering a lot of the things that you need to know. And I know for sure we cover everything that you need to know to get into research labs on campus. Yeah, so I'm actually going to extend the break a little bit longer until 6:05. Oh, whoops. But yeah, and then, so does anyone have further questions? Yeah, sorry, Corey. Apparently, I didn't publish the most recent edition. It's running right now, and it should be done in the next 2 or 3 minutes. Sorry. That's part of why I extended the break. Okay, so what I'm going to do while this is running, I'm going to actually answer the question that I was asked earlier, just so we're not sitting in silence. So getting into research over the summer. So actually, okay, so for anyone that's interested, this is for summer programs. I believe, yeah, so this is slide 60 on the deck that I gave you, or the link that I sent. So essentially, the summer programs are normally sponsored by the NSF, National Science Foundation. They're called REUs, Research Experiences for Undergrads. And there's basically a massive list. Is this link? Okay, yeah. So on that particular slide that I was at, so slide 60, what you're gonna want to look at for the list is go to that particular link that I have right there, which will take you to the correct slide. But basically, you're gonna spend 8 to 12 weeks at some other institution. They'll give you some kind of stipend, and they're going to pay for your travel and housing. The travel is up to like 500 normally, although I don't know how that works for COVID. I think most of them have transitioned to just like online experiences, but you'll still get a stipend for sure. And so, like it says, they vary by program, but normally the stipend is somewhere between $4,000 and $6,000. So while that is very low compared to what you get out of an internship, oftentimes you can normally turn, especially if you're doing computational work, you can normally turn a summer program into an actual publication, which, although like, I don't know if it makes up everything in terms of what you get at an industry internship, it will definitely make getting into grad school, especially if that's what you're trying to do, it'll make that much easier. And it'll basically start bumping you up to the point where you're easily able to compete in the top 10% of your applicant pool. The reason why the top 10% is important is because once you're in the top 10%, you kind of have to like rescind control over your application. There's not much more that you can do. It basically just like falls to random chance, which is like, it really sucks. But the point is that once you're in the top 10%, it's like your application is entirely out of your control. There's nothing that you can do. Whereas until you get to that sort of threshold, there is something that you can do to make your application better. I don't know if that makes sense. Hopefully, like you take solace in that, or hopefully you learn to take solace in that in some way, because yeah, it's a very real thing as far as I've seen. So yeah, so these applications normally open right around now, and then they'll close somewhere between January and March. For the ones that close in January, you'll normally hear back by March. For the ones that close in March, you'll normally hear back by May. So it's about a 2-month turnaround. And then these are essentially 3 things that you should really look to get out of summer programs. I've already hit on these 2 of a research-oriented recommendation letter. That's important for grad school. So yeah, and I honestly can't state, like I can't overstate the importance of having research-oriented letters of rec for grad school. Those are arguably the most important things that you will submit on your application, on an application to graduate school. And then hopefully you end up with either a peer-reviewed conference or journal paper. But the way that that'll normally work is like you'll spend like 4 months or so, or sorry, not 4 months, 2 to 3 months. You'll spend 2 to 3 months at whatever this institution is working, and then over the span of the ensuing, like, I don't know, 2 or 3 months, you'll probably be finishing things up, and eventually turning it into a paper typically, and then hopefully submitting it and getting it published. But I would argue that this is actually one of the most important things, if not the most important thing for those 8 to 12 weeks, is getting mentorship from non-UCF faculty. And that is essentially just like broaden your horizons. The faculty, like everyone that's a faculty member at any institution, they're already a world-class researcher, especially if they have tenure. That's a requirement. But they are also like, they all have unique and very, and in some cases, they're very, yeah, so they have unique and sometimes very extreme perspectives, and they're also relatively pedantic. So if you can get through that, then you can learn a lot from almost all of them. There are some where you'll probably learn less. There are some where you won't learn anything at all because they're assholes. But at least in my experience of 5 research mentors, I think only 1 was. So for now, like, I don't know, batting average 0.8, which is pretty damn good. I don't actually know baseball, so I probably screwed the average up. So Nathaniel asked, what sorts of qualifications do they look for in summer programs? It varies from program to program. So some programs are like, you're fresh, you haven't done any research whatsoever, that's okay. That's normally what REUs are tailored for. But typically what will happen is the split for REUs is normally going to be about half of the applicant or about half of the accepted people have done research of some kind, and then the other half haven't done anything. And the rationale behind that is to basically have like this sort of tiered mentoring, where you, the person who's done at least a little bit of research, can help your teammate typically, especially if you work in teams, can help them sort of get acclimated, and to start really picking things up. And also because like in some programs, they set some pretty high expectations. And if you throw someone who's never done research, if you throw them into a program, set the bar exceptionally high, they're probably gonna, like, it's very rare that they won't fail. And that's not like a fault of their own. It's just like, you guys designed a shitty program. But all of that to like concisely answer of it varies from program to program. The one at UCF, so I think there's a CRCV REU. So if I actually go here, yeah, so there are 2 REUs for UCF. So there's that and that. Yeah, so program dates for the Internet of Things REU is May 18th to July 10th. Although that was for this year, so probably like, I don't know, shift the dates by like a day or 2, maybe a week tops, but yeah. And then for the CRCV REU, that one, I believe they care a lot about your GPA. That's what I've gathered. So yeah. And then for the question about getting into summer programs, go to this link. This link should be fixed now. Yeah. And then you can search for all of the programs by what kind of field you want to do, and so on. So yeah. Okay, so now let's see if this is published. Oh no. Okay, so I will let you know when this is published, but I'm going to start working through it just because of time. I'm exceptionally sorry about that. Okay, so sort of moving on to the workshop. Yeah, so okay, we're going to go ahead and import a few libraries, so namely NumPy and Pandas. For doing machine learning and data science, those are actually going to be sort of your bread and butter libraries, but I'm not going to spend a whole lot of time covering them at the moment. Wait, what? Oh no. Okay. So actually, okay, can someone go ahead and head over to this particular link? It should be in the slide deck, which I linked earlier, and see if you can make a copy. It should be like, so where I see edit, you should see copy or something of the sort. And then can you post in the Zoom chat if it actually renders into something that looks along the lines of this? Because if it does, then we can go ahead and do that. Okay. Yeah. All right, then I guess I'm just gonna have, because apparently I can't run two things in parallel. I can only run one of them. So what I'm gonna do is I'm gonna go ahead and just do everything here. Sorry. Yeah. So, okay, so what I'm doing here is I'm importing some libraries. And so libraries I'm importing are NumPy and Pandas. So essentially NumPy, you can think of it as really fast arrays, and Pandas, you can think of it as Excel, but better because you can use programming with it. And also because you can do things that Excel can't, like run it across multiple computers or run it across multiple cores on your computer. So yeah, these are standard libraries in Python. You can look them up. They're basically just like, how do you maneuver across a file system? Why is this? Okay, hold on. Okay, so, all right, sweet. So now it's working. Yeah, so all that this snippet of code is doing is it's just walking through the directory. So basically what it's supposed to be showing is right now I have the 60,000 Stack Overflow questions with some quality rating. That's the data set that we're mostly going to be looking at, but there's also a Lego figurines data set. So if you wanted to play with like image classification and things like that, you can also go ahead and do that. So Stack Overflow, like I said, 60,000 questions. They're collected from 2016 to 2020. High quality, like it says, you scored at least 30, and you haven't made a single edit. As far as I've understood for that, all that means is that there's never been an edit on the post. Low quality post with a negative score and multiple community edits. I don't know what multiple means in terms of number. I'm going to take it as obviously though at least one, but they're still open, and then closed are posts which have been closed. And so presumably, like if you wanted to deploy this like in production or something like that, what you could do is once you've trained this model, you could actually go and start just like walking across. You could start walking across Stack Overflow's website, and then potentially you can basically, so potentially you could then use it to predict like, oh, is this question going to be closed? Is this question going to be a high quality one, etc. And so obviously, like presumably you could do this like by eye, just by like manually inspecting the questions. But I don't know if you've ever tried to like scroll the web, like go through the web at like, I don't know, 1,000 pages a second. But computers probably do that a lot better than any one of us do. So yeah, so all that I'm doing here is I'm just saying, hey, grab me the Stack Overflow quality data. So then this is a function that I've written, which basically what it does is it reads it in. So it loads the data in file name. It's going to show you the first 5 rows in this case. And then we don't need the ID tags or creation date columns. And can you convert these string labels that they give us? So high quality, low quality edit, low quality close. We're going to convert the string labels to numbers. And that's just because computers don't understand English or any language other than like machine code. So as a result, this is what we end up with. We're not going and so when this is actually displaying, what you're seeing it before I actually drop these columns and before I do any of the label like recreation. So this is some like numeric identifier, don't really care. You have a title, so like in this case, as you can read, and then it looks like this is actually an HTML rendering, and kind of cool, but it might get in the way, but we'll see. And then there are tags and a creation date. So that's another thing that you could do, is you could potentially do some kind of like clustering, for instance, with the tags, where it's like, okay, now let's look at all of the Java related Stack Overflow questions and determine, okay, what's the relationship between Java related questions and low quality questions that have been closed? I promise I'm not saying anything about people that like Java. And so you could do something like that, or you could look at Swift or Android or whatever other number of tags, but I happen to throw them out because that's not what we're going to do today. But yeah, so you can basically get just like as creative as you want with these kinds of questions. So clean and condense, what that's looking at is, so this is actually doing a little bit of like, not quite advanced pandas, but it's definitely moving in that direction. And so what's happening here is I'm actually saying, I want to select, I want to select the columns in to condense, which in this case are going to be a list, as you can see. And what I want to do is I want to actually run the string.join. So let me show you like an actual example of string.join. So let's say we have don't ask what goes on in my head. So all that does is I took this list and I've now joined them with a space and I've created a single string. That's all that the parenthesis, or rather, sorry, the space in quotes dot join is going to do. What I'm saying in terms of axis one is equivalent to rows. I don't know if it works in ag, it normally doesn't. But all that means is what it's going to do is instead of going column by column, so instead of doing like this operation across all of the column of title and then all of the column of body, I don't want to do that. I want to do it row wise where I fuse the title and the body together. And so that's why I choose axis one to operate over the rows. Yeah. And then the next thing is I want to turn everything from some form of capital case. I want to turn it into lowercase. And so that's what this dot lower function does. So you need to do this dot string for pandas to like treat the entire column as if it's a list of strings. It's a weird quirk, but it's really nice when you need to be able to do string related operations. So yeah, so basically treat call as a string, then lowercase it, lowercase everything. Then what we want to do, so this is regex. For those of you unfamiliar with it, it's something that if you want to do NLP, you probably want to know. So with regex, what we're basically saying here is I'm saying anything that is not in the range of lowercase a through z, so the alphabet, or uppercase a through z, the alphabet, or it's not a space, I want you to delete it. So the point with that is when you have something like this underscore, or you have something like this colon, or you have something like an angle bracket, or you have this shit of just like apparently somebody on Windows coding, or you have that. So you have a hashtag or something like that. I want to nuke all of them and just get rid of it. And so yeah, so now that we have that, now we can actually create a text column. So we're going to create the column in the data frame. And then what we're going to do is we're going to return the column and where we've dropped whatever we've condensed because we don't want it anymore since we're going to feed it into our machine learning model. So drop the uncondensed columns. And then once we've done that, now we can apply it to our training data and our validation data. And so something to clarify. So the whole idea of training and validation really has to do with like when your professor gives you a cheat sheet, or not a cheat sheet, a like practice exam. Presumably, they're not giving you an exam that directly mirrors like question for question what they're going to give you on the test. And so that's this idea of trying to test generalization is, do you understand the concept rather than the exact mapping? And so I think like now maybe you might start seeing like, oh, well, maybe this is where supervised learning starts falling apart because supervised learning learns direct mappings from an input to an output. Whereas when you want to test something, you're trying to see, do you understand the input to output map, or do you understand the concept that I'm testing for, which is giving you that map? If that's unclear, let me know, and I will try and further clarify that because that's actually a pretty important concept. So I'll hold off on progressing until I've gotten at least one yes or no as to whether or not that's clear. Okay, sweet. So yeah, so now we have this just like fused text column and this y value. So the y value is going to be our label. So we've converted it so that like 0, I believe, was high quality or something like that. No, 0 was low quality closed, high quality or low quality edit, and high quality is 2. Okay, cool. So now what we're going to do is I'm going to just go ahead and split everything along the columns. Splitting everything along the columns basically allows us to just pass in individual arrays, or in the case of like in Pandas land calls these a series. So what it's going to do is it's just a list of basically, so like in this case, the title was probably something convert list string to string in C# or something like that. And then, so if I were to actually ask Python, what type is this? It's going to tell me that it's a pandas series, which just represents a single column. So you can also just think of it as a list, and that's a function, like that's perfectly fine. So we're going to use this idea called TF-IDF. So basically all that looks at is, like it says, it's assigning a word frequency score. And so what that's trying to do is it's trying to highlight words of greater interest. And the way that you look at this is by seeing what are the words that are in the document. So in the document would be, in this case, something like this. So this would be a document. And then this is another document. And so you're looking at the words that are in document versus across the documents. So what words are unique to this document, but aren't unique to this one? Or rather, yeah. So what words are unique here? What words are unique here? And then what words are shared? So for instance, easy ones are Java apparently shows up at least once in both. And so what TF-IDF is doing is it's tokenizing the document. So it's converting them into numeric values, learning the vocabulary, and learning what's called the inverse document frequency weightings. And so the idea with that is once you've built up this vocabulary over the documents, now you can learn how to actually encode new documents that you've been given. And so what that's looking at is, for instance, here, where we start out with a TF-IDF vectorizer, we do, so this is actually a fused function. So the other way to do this is vectorizer fit train X. Yeah, is to do this instead. And so where we basically do a fit, so we're saying, hey, TF-IDF vectorizer, go learn the vocabulary, go learn all of the words that exist in this data set from train X. And now what I want you to do is I want you to transform this data set. And so in transforming this data set, what that's going to do is it's going to give us the ability to represent the words as numbers or as frequencies in this case. And by representing them as frequencies, now we can pass them to a machine learning model, because the machine learning model easily takes in numbers and it's like, thanks for giving me all this food. Whereas if you give it words, words are inedible to a machine learning model. So that's just some stuff to basically tell Python not to yell at us. So yeah, okay, so this is basically the meat of the training loop, and I will come back to explain what's going on here, because it's actually going to take a little bit to run the rest of these models. So what we're looking at here is we're looking at something called logistic regression. Logistic regression is a form of classification, or it's a type of classification model. So actually, before I keep going, does anyone have questions of any kind? Because I don't necessarily see hands raised or anything. So I want to make sure that most everyone is tracking in some way before I start jumping into like, hey, here's a bunch of machine learning lingo. I'm going to take the silence as everyone is following. Absolutely. They could teach this tomorrow. Is that a safe assumption for me to make? If you say no, that's okay. I just want to know. Okay. How about today? Would that be better? Okay, that's fair. Yeah. So, okay, cool. Yes, Pablo. Okay, so so logistic regression is a form of classification. And so all that we're doing is we're doing classification today. We're not going to do any regression, but something that's actually kind of cool. Okay, one, ignore the fact that this is regression. I'm not lying to you, I promise. So then I'll actually tell you the cool thing in a bit, to not be too potentially confusing. So yeah, so like the tin says, multinomial logistic regression is a generalization of this idea called logistic regression. So logistic regression is essentially, since I for some reason didn't put a picture, okay, so nope, that is a sigmoid function. So the sigmoid function is basically like, if memory serves, the sigmoid function is sort of like the parent of all logistic functions. And that's what it's called. It's part of a class of functions called logistic functions. And so logistic regression leverages a sigmoid function. And so what that's supposed to do is it's basically supposed to take really large values and squash them down into something between 0 and 1. And in squashing them down into something between 0 and 1, what that allows for is it allows for very large values to not essentially dominate the model in terms of how it's starting to combine everything, because all of these models basically rely on multiplication. And so in an effort to not have like massive values multiplied by more massive values just growing in size, the logistic function allows you to actually squash them into something that's more reasonable. So one of the things that you'll see with this is that if we, okay, that looks pretty bad, but if we zoom in, what you'll see is between like -5 and 5, those values tend to change quite a bit, right? Whereas once you start going past 5, at least up until 10, it seems like you're already pretty close to 1 here. And then as you move over to 10, you've gotten a little closer, but the amount of change between the value of, between an input of 5, so that's what this Z is, between an input of 5 and an input of 10, it doesn't change it all that much. And so that's really what I'm trying to get at. Of it takes really large values and it tries to mute them quite a bit so that they don't cause too much havoc in your model trying to learn how to be able to multiply these numbers together. Does that make sense? That might be a little vague. Okay, sweet. So multinomial logistic regression is just trying to generalize that, because logistic regression right now, like as it stands with using one sigmoid, will only work on what's called binary classification. Binary classification is basically where you're saying yes, no. So you're splitting it into one of two classes. And so having multinomial logistic regression allows you to handle multiple classes. And so, no. And so typically what this means is that, so typically logistic regression works really well when you can linearly separate your data. And so that goes back at this idea of what's called linear regression. And so linear regression in the context of machine learning, not the context of statistics, which are different. In the context of machine learning, it's looking at how can you basically represent your data in a straight line. Statistics looks at it from a slightly different angle. It's a very nuanced angle, but it's an important one that I'm not going to go into today. But what you're looking at is when you have data which can be fairly well separated with a line, then what that allows you to do is you can then basically treat it as, now I can classify yes, no, or something along those lines. And so We're going to talk about naive Bayes in a second, and we're going to talk about random forests. It's definitely very sensitive to the balance of the classes. And so what class balance looks at, so just so I can give you an idea. So class balance is going to look at something like this. So no, hold on. So we're going to look at our labels, and in pandas, we can do this thing called value counts. So what value counts is basically saying is I'm asking, okay, in Y, what are the unique values and how many of them are there? Hence value counts. Programmers are super creative. So what this is showing is that we have 45,000 values and we have 15,000 in each. If you want to make it a little bit easier to understand, we can do normalize, and it's showing that everything is 33.3%. One of these rounds up, but that's okay. Actually, no, it doesn't. Never mind. So point is, though, is that we have an equal class distribution. And because we have an equal class distribution, that means that we're fine to use logistic regression, just like on the assumption that that shouldn't matter with making our logistic regression models. And it shouldn't have a huge impact in terms of its ability to handle data it's never seen before well. And so in this case, multinomial logistic regression is going to generate pairs of logistic regression models. So like I said before, where logistic regression models can only handle they can only handle separating two classes of data. In this particular case, the way that's being used, it's going to create pairs. So what that actually means is it basically creates three models where on one of them, it's comparing the classes 0 and 1. On the other, it's comparing the classes 0 and 2. And on the last, it's comparing the classes 1 and 2. And so what it's then looking at is the vote. It's basically looking at a voting system. So essentially the maximum score, the maximum vote that any of these classes can get is 2. And that's what you need to win. Or rather, not to win, but rather to be the proposed solution. And so that's essentially what's happening under the hood here when I'm saying, hey, give me this logistic regression model, and then I actually go to train it, which I'll talk about in a second as this is running. And so for more logistic regression stuff, look at that website, which you'll have access to the moment I can actually save and upload this. I'll send something in the ACM Discord or ACM-W Discord about that once it's done running. So I'm actually going to go ahead and run everything because I'm not changing a whole lot. But what's going to happen is, so I was calling this function train and grade. So what we're doing is I'm passing in, so like it says, I'm passing in this log reg CLF. All that means is logistic regression classifier. And so I'm passing in some training set, which is my training data. So my training X, which is my training data, and my train Y, which is my training labels. That's just nomenclature from machine learning. And so I have my testing set as well, which is validation X, validation Y, which is to test our training results. And then logistic regression is just the name for the plots. So I pass in the training and testing sets. I break them apart because they're tuples. This is something that's nifty and kind of, I've only really seen it in Python. I think you can do it in a few other languages, but it's not super important. So yeah, so then I have this training bit, this train function, where I give it the model, I give it my training label, my training data and labels, and then I give it my testing data. And so what's going to happen up here is I'm now, so on line 3, I'm saying, I'm defining the function. On line 4, I'm saying, hey model, go fit yourself to this data. And so this is where logistic regression is like, all right, I'm going to spin up 3 different logistic regression models, and I'm going to create this voting structure. And it's going to do all of that behind the scenes for you, which is great. Because as like researcher, engineer, whatever, you don't really want to deal with that unless you're trying to deal with it so you can learn it and improve upon it. But if you just want to get something done, this is great. So pass in your labels. It does all of the logistic regression voodoo behind the scenes, which you should definitely look into, but not right now. And so I'm then going to hand the model, which is now trained. I'm going to hand it this new data that it's never seen before, and I'm going to ask it to predict what the labels are. And so that's what this preds value is it's the predictions. And so when I go to grade the model, I'm going to grab the confusion matrix plot and a classification report, which are two things from scikit-learn's metrics library or submodule. I'll explain what the classification report and the confusion matrix are in a second. And so what's going to happen is I'm going to also score the model on its training and testing, or on its testing data. And so that's what this output value, where it says test accuracy of logistic regression, is 87.49%. So what that's saying is on the testing data, I correctly classified 87.5% of all the data. And so this bit right here, actually, before I go on and explain what these things are, is anyone lost in all of this code in a way that's like, holy shit, I'm never going to understand machine learning now? If you are, I need to know, because I can actually like help you like realize I was there too and everybody else is there at some point. Okay. Keone, is that pronounced right? What is there, like, is it a function? Is it all of it? Is it one specific bit? Also, I think you can just like turn on your mic and you should be fine, in case typing is laborious. Okay, so then I'll just go ahead and annotate all of it in a little bit more detail, but also like to everyone, you can ask me questions afterwards about this too. So yeah, but basically so this kind of goes back to what I was trying to get at here. No, with this. So when I have this, so what? That's not going to work. Damn it. Okay, so we have this data set. So I'm going to hop back out of the code and I'm going to go back to sort of a conceptual view. So in the data set, I have this like train data and I have this test data. So let's ignore the test data for a second and let's just talk about the training data. So on the training data, I have this train X, which I can also just call train data, and then, or better, so it maps to the slides, train input and train, oh my God, labels. So train inputs and train labels. So that maps to this idea of inputs and labels. And so now what's happening is I want to take this and I want to take, so if we ignore this like function, nope, and I just go ahead and actually write all of this out. So I have this model, which is that little orange circle, right? So this model, now I'm saying, hey, I want you to fit to the train inputs and the train labels. And so by saying, hey, model, I want you to fit, what it's actually going to do is there's this basically like magical process. Let's see if I can insert a, oh no. Yep, that's gonna have to do. Okay, so nope, screw that. Okay, so let's see. Sorry, I'm trying to do some drawing on the fly to hopefully make things a little clearer. So what's gonna happen is here, you're gonna have, so actually, now red, with the right arrow, yes, cool. Nope. And sure, that seems fine. Okay, so what you're gonna have is you're gonna have this process where you go and so the model will go and along this green line, it's gonna make a prediction. And so when it makes a prediction, there's a process that goes on behind the scenes where it basically spits out for every single bit of training input, it spits out a label. So that label could be 0, 1, or 2 in our case. And when it spits out that label, then So that's what its predictions are. That's what the model predicts as an output. But we also gave the model the actual labels for our data. And so what the model is going to do is it's going to do a comparison between the inputs that, or rather the predictions that it makes is going to do, it's going to do a comparison between those predictions and the actual values that we have. And when it does those predictions, they do some fancy math, and that fancy math that they do spits out a distance between the points. And the distance that it spits out can then be sent back to the model along this red line. It gets sent back to the model, so the model learns how to make those updates. And there's a way of quantifying it. I'm not going to go into it just because of time, but there's a way to quantify how much of a change you need to make. And so this is like as a broad idea is called the credit assignment problem, or leads into it. And so what that's trying to get at is it's like, imagine that you're talking to like a group of friends, and one of your friends tends to be not like terribly based in facts, let's say. And so when they're not terribly based in facts, maybe at first you didn't really know this about them. So you kind of took what they said and you sort of took it at face value. You didn't really think much about it and you didn't really question it. But then over some amount of time, you start realizing this, and you start realizing that they're wrong more and more of the time than they are correct. And so as you're realizing that feedback that you're getting, that's what that red line is. It's the feedback between them being correct in what they're saying and you're like weighting what they're saying. And yeah, and so what you're optimizing there is you're optimizing how much like sort of trust or faith you put in their opinions or in their views or whatever. And that's the thing that you're optimizing. So that you can kind of think of as that's the model that you're optimizing right there, is how much faith do you put in that friend's statements about stuff, because they don't tend to be factually correct. And over time, you might start weighting them lower and lower in terms of how much you take what they say at face value. And it's like, oh, I can trust that, versus questioning it potentially severely because of the way in which they're incorrect. Does that help in terms of making a little bit more sense, or does that make it more confusing? Okay, sweet. So that's what's happening in this fit function. It's just that it's abstracted away. And part of the rationale for doing this is because what I explained was a very like hand wavy explanation. There's a lot more to ground that sort of idea that honestly you need to go learn on your own. Or just like ask people that like know the stuff to clarify those kinds of things. But yeah, so all of that to note that and that. So that's what's happening in this train function. And then all that I'm really doing is I'm essentially doing the first part of that fit portion where I'm saying, hey, here's some data. Now predict some labels. So make a prediction. That's all that predict function is doing, is I'm saying spit out some classifications given the data that I just sent into you, model. And so what happens is when I do that, then I can use those predictions and I can compare them to the actual values that the test data has. So here, just to be concrete. Okay, so I can go and compare that on the classification report, and I can compare that on the confusion matrix. And so I'm going to go and sort of elaborate on what these mean. So okay, just to be sure. So technically, like officially, there are like 5 minutes left. On the form responses that I read, there seemed to be about half who were willing to stay an extra hour. So I'm willing to stay an extra hour and finish going through all of this and then answering whatever questions. For those of you that want to stay, I'm just saying, like, point is, you don't need to feel bad if you need to go or if you want to go or anything like that when it's 7 o'clock. So, or even now. So, yeah. Okay, so the classification report is computing this weird thing called an F1 score. So what an F1 score is looking at is it's looking at these ideas of precision and recall. So the idea of precision, oh no, of course it disappears. So the idea of precision is when you're labeling things, it's basically looking at the true positives. So how often do you label things correctly when you label? Yeah, so how often do you label things correctly? Whereas recall is looking at how often do you okay, hold on. Before I butcher that, I'm going to check my understanding just to make sure, because for some reason I'm forgetting. Okay, yeah, so so I guess like I'll bring this up here so you can see it as well. So what F1 is looking at is this bit right here, so the picture. So essentially your precision is how many of the items that you've selected are relevant. So when you look at the true positives and the false negatives, so the true positives are the things that you said, like it belongs here, and then the false negatives are the things where you say it doesn't belong here when, or no, sorry. So yeah, so true positives and false positives are looking at with where you label something correctly because it belongs in this class, and where you label something correctly when it did belong in that particular class. That's what the false positive is looking at, where you essentially say like, hey, you belong in this class when you really don't. And then true negatives and false negatives are when you basically go about saying, so with true negatives, it's where you label something as not in this class and it's not in the class. Whereas a false negative is where you say it's not in the class, but it is. And so that's distinct from a false positive where you're mislabeling something by saying it's in this class, whereas a false negative is saying you're mislabeling by saying it's not. And so that's looking at this circle is everything that belongs in the class that you're looking at. So how do you do on guessing that? And then how do you do on actually delineating between, in that particular class, the things that belong in it and the things that don't? It's kind of an abstract sort of idea. I don't have time to more concretely ground it, but it's a better measure than accuracy, because accuracy looks at an absolute value of how often do you label things correctly. Whereas an F1 score is looking at how well do you draw the boundary between the things that you're supposed to label correctly. Yeah, so with an F1 score, you're looking at how well do you draw that boundary, and if you do that, if you do one thing particularly well, how do you make sure that you do the other? Because that's the whole idea of precision and recall, is they tend to work against each other. So normally when you'll see a model that does really well with precision, it may also do poorly with recall. And so an F1 score tries to quantify that so that you can basically try and push both forward, because it's a hard problem, but it's a worthwhile one to do. So for Nathaniel, so we want all true values. It's not so much that we want all true values, we want all true positives and all true negatives. So the idea is we want to make sure that we correctly classify things. So when you have a true positive and a true negative, it means that you have correctly classified the thing that belongs in that class. Whereas if you have a false positive or a false negative, you incorrectly classified things as not belonging to that class. So the idea with that is So to kind of put this more into like the thing that we're dealing with, where you have like a high quality Stack Overflow post. If you say that it is a high quality Stack Overflow post, and it indeed is a high quality post, then that's a true positive. But if you say that it's not a high quality post, and it indeed is not a high quality post, that's a true negative. And then here, so just so I have the picture up so everyone can see. So if it loads. Okay. What? Okay. So, oh my God. Okay. So yeah. So true positives in our case are going to be high quality, and it indeed is high quality. Whereas a true negative is going to be you said it's not high quality, and indeed it's not high quality. Whereas a false positive is where you say it is high quality, but it indeed is not high quality. And then false negative is where you say it's not high quality, but it indeed is high quality. Does that make sense? I said a lot of things in very similar ways. So if it doesn't make sense, let me know. Okay. So it's the sort of thing where I certainly don't expect like anyone to truly understand an F1 score. As you can tell, like I don't exactly remember it. I just know what I have the vague intuition of what it's supposed to do. And I know that maximizing your F1 score is always good. At least when it comes to reporting things to people. And so, right. So what this is looking at is, so like it says, we got an 87%. Yeah, no, it's great. I'll put it in the appendix as well, so that you guys can also like look at it later. So yeah, so basically what we're looking at here is we're seeing that on class 0, so on low quality close, the model gets about 85% precision. So it's classifying the relevant information. So it's selecting it's basically correctly classifying the information that's relevant. So in class 0, it's saying it's getting about 85% of things correct. So it's basically making, yeah, so it's potentially approximately 15% of the data in class 0 or low quality closed, it's incorrectly classifying. Those are the false positives where it's saying that it's not part of the class, but it actually is. And then for recall, what it's doing, so it's getting an 80%. So that's supposed to say of the values that are in class 0, it's saying that, yeah, so, okay, just to make sure. So here, you're saying that 85% are in the class, and they actually are. And it's saying that 15%-ish are in class 0, but they aren't. I'm making sure that that's very clear. But for recall, what we're saying is instead, 80%-ish are in class 0, but then we're saying that about 20% or so are in class 0 when they're not. Does that make sense? Or sorry, no. It's not, we're saying 20% are in class 0 when they're not. We're saying that 20% aren't in class 0 when they are. Yeah, it takes a little bit to get like a proper understanding of F1 scores. And as you can tell, it still can trip people up. But anyways, so like at least for our cases, realistically, and accuracy is perfectly fine. And so there's naive Bayes, and then there are a few other ideas. So if you're familiar from stats with the idea of Bayes theorem or Bayes rule, that's what this is. Where all you're trying to say is, I want to find this out. And yeah, so I want to find out what the probability of the event A given that I've observed the event B. And so that in lingo is the posterior. And so what you're saying is, I've already observed and I know the probability of A, which is the likelihood of A in this case. So I know the probability that event A happens. And I also happen to know the probability that event B happened given that I saw A. And then I also happen to know the probability that B has happened as well. So the idea here is, okay, I know the probability that A happened, given that I've seen B, and I want to take that and I want to weight it by the probability that A even happened at all. But I also want to make sure that I have correctly reshaped my probability, I've correctly normalized for the likelihood that B actually happened. Because, and so the reason why that works is, what we're trying to say is, I've observed the opposite happening. And so now I can adjust that to be probability of A given B by weighting the probability of this event, of this likelihood that I've seen, by the probability that the event that I observed even happened. And then I can normalize it by the probability of what I just saw happen actually happening. Does that make sense? I may have tripped up on words there as well. It's also completely okay if like Bayes' rule doesn't make sense. It's something that takes a while to like really like understand intuitively. And it's one of the hardest things I've ever had to explain to most people. So yeah. What do you mean you're in the chapter of the, oh, in like a probability class? Okay. Oh, okay, my bad. Okay, makes sense. Yeah, so so like I said, a lot of these things are going to be things that like they'll take time to really understand, at least at an intuitive level. I would argue that unless you're trying to, yeah, unless you're trying to do machine learning or statistical theory, an intuitive understanding should get you far enough. Eventually, you're gonna have to break that wall of like intuitive understanding is not enough. But even like now, I haven't broken that wall yet. So at least for this. So I think you'll be fine. So there are 3 types of classifications. We're going to be using multinomial. So, nope, god damn. Okay. So a Gaussian is normally used for classification tests, but it assumes a normal distribution of your data. And so I haven't confirmed that the data is normally distributed. Frankly, I'm not even entirely sure how to do that with text. So we're not using a Gaussian for that. Bernoulli is just a binomial model. So if you take, I think it's like probability and random processes or something like that. At some point you talk about Bernoulli probabilities. All that's looking at is like flip a coin, heads or tails. That's a Bernoulli probability of, and then you can basically do that to figure out like what's the likelihood that you get like 10 heads in a row and things like that. Yeah, although you don't like that class, Chloe. Like, that's not to dissuade anyone from taking it, but yeah. And I think one of the statistical theories, either statistical theory 1 or 2, teaches it. Because probability and random processes is like a combination of stat theory 1 and 2, but it drops some stuff. But like the point is that honestly, like if you want to do machine learning, you're probably not poorly served by just taking a statistical theory class. And if you have a solid professor, like they can actually be kind of fun. Otherwise, like you have to kind of make it fun for yourself, which is kind of a pain. But yeah, so we're going to end up using multinomial probabilities. And part of this is because instead we count. Apparently I can't spell. Yeah, so we're going to be looking at multinomial probabilities because of the way that we're using TF-IDF, where we're looking at frequencies of word counts. So we have the actual number of times that it occurs, and it's a weighting. So what we end up seeing though is that naive Bayes actually does pretty shit in comparison to logistic regression. And now this is something that's normal. So what I mean by normal here is some of these models are good, some of these models are bad. I would argue that the main reason why naive Bayes is not so good in this particular case is because naive Bayes actually assumes that all of the words are independent of each other. And so what that means is when I'm asking a question, like for debugging, I don't know about you, but like the words that I use when I ask those questions, if I were to just like dump them into a bag and just randomly pull words out, or like rearrange the order of my question, odds are my question's not going to make a lick of sense. Whereas here, and so like that's the problem with naive Bayes is naive Bayes is dumping all of the words into a bag, and order doesn't matter. I wouldn't necessarily say that. Yeah, so I wouldn't necessarily say that logistic regression is actually like avoiding that, but I know that that's what naive Bayes does, where it looks at the frequency of words and you'll get the same value if you have the words just in a different order. You'll get the same probability, which is really what I'm trying to get at. And so if that doesn't make sense, I'm also going to link a few videos as well that do a pretty solid job of explaining these things. So yeah. So then there are these things called decision trees, which apparently I've just described as decision trees. So what decision trees actually are, so you can think of decision trees kind of like your control statements in like a program. So where you have like if, else if, else if, else if, else, or whatever. So with decision trees, what you're trying to do, and so I'll just use this. So with decision trees, you have this one thing that you start from, and it's like, okay, I'm going to figure out something that splits this data as much as I can so I learn the most from it. And then based on that one feature, that one piece that I can split on, I can now go ahead and go to the next layer in the tree. And I can go down that branch to the next node. And once I go down that branch to the next node in the tree, I can then figure out what's, based on this, what splits the tree so much to give me the most information. It's this idea called information gain that really drives decision trees. And so information gain is looking at trying to quantify, when I split stuff, how do I learn the most about my data with just splitting on one feature? So in this particular case, it's going to be splitting on more so like frequencies of words. It's kind of hard to like really think about this with language, but somehow it works. And so the point is though, is that you're looking at splitting your data into essentially, you're looking at basically doing, it's not quite a binary search, but something analogous where you're looking at splitting your data in half or better if you can, based on looking at one isolated feature. And so a feature is just a way of describing your data. So like, for instance, if you had something like college admissions, and so let's assume that UCF only cared about your SAT scores or your ACT scores and your high school GPA. That means that there are two features describing you that plot you on an XY coordinate grid or an XY coordinate grid. And based on where you land there, if they draw a line, you either land above or below the line. That determines if you're accepted or rejected. So the points, the values that are being used to plot your point on that two-dimensional grid, that's each one of those are a feature. Does that make sense? So that idea of features, like, does that make sense how I'm describing it? And can you like kind of generalize that to like n features? I need a yes or a no, or maybe. Okay. So when you say, okay, so what's hanging you up when I say that features are looking at, like, in the case of an SAT or something like that? Yeah. So what's tripping you up with that? Okay. So all that I'm trying to get at here is, so let's say that, so let's ignore the fact that you can take an SAT or an ACT. Let's just say that you took the SAT. So for this case, I think this is UCLA's. Yeah. So this is for UCLA. So what they're saying is, so ignore the coloring of just like accepted and denied. But one of the things that you'll notice just by looking at this clusterfuck is that you can't actually like split it very easily. Like it's not clear what the function that UCLA uses when it comes to GPA and SAT. It's not clear. But the point that I'm trying to illustrate is that with this, where you're only considering two features of a student. And so those two features that are being considered here and being illustrated are their GPA and their SAT score. And those two features presumably would explain admission or rejection. Clearly it doesn't, but let's ignore that fact. Does that make sense? Like, does that clear things up at all or no? If it doesn't, that's okay. I just want to make sure, like, I just want to know. Okay, cool. If it doesn't, like, I'm sure that in reading about all kinds of stuff relating to machine learning, it'll eventually start clicking. And so what we're seeing is that, like, naive Bayes did pretty poorly, decision trees did pretty poorly, and I would argue that that kind of makes sense. And the rationale as to why it makes sense is because we're dealing with text, and as far as I recall, the decision tree classifier is only going to build one decision tree. Building one decision tree that's exceptionally deep is like, sure, maybe it'll work, but the problem is that eventually you get to a point where you can't handle the nuance of, most likely, the language that's being used. And so that's something to like balance. And when you have something potentially as nuanced as language, you run into this problem of generalization. You need to be able to generalize to things that you haven't necessarily seen before. And depending on how this tree is actually structured, it's probably going to be pretty hard, which is why I would argue that it kind of makes sense. Although you have this weird result with class 1. Not entirely sure how that worked out, where it practically nailed class 1. So low quality, but it was open, or was left open. Not sure how it nailed that, but apparently it did. Because like you don't really see nailing like that even for naive Bayes. But anyways, so these are also questions that like I would honestly like encourage you to try and answer on your own time as well. Is like, why is this model doing this quirky thing of like doing phenomenally well on one class of the data, but not on all of the data? So yeah. So random forests are just taking decision trees and scaling them up. And so I would argue that it makes sense as to why random forests actually end up working better than decision trees, partially because instead of trying to make this really deep tree, instead we're going to make some more shallow trees, but we're going to split the trees apart. And by splitting the trees, what that allows us to do is that allows us to have trees that specialize, and we use that specialization of the trees to act as a voting mechanism in the same way that we did with logistic regression. Does that make intuitive sense? I don't expect it to make technical sense. Sweet. And then, so again, like there's more to random forest than this, but I'll elaborate on that in the appendix. So the last thing that I'm going to show you is this idea of gradient boosting. So gradient boosting is what's called an ensemble model, just like random forests. So the idea behind ensemble models is rather than have this one like monolithic thing that does phenomenally well, instead you have multiple weaker models that aren't necessarily as good, but you combine them together. And in combining them together or giving some kind of voting system that allows it to do better than just one singular model would. So yeah, and so kind of like elaborating on this, it uses an idea of like divide and conquer in the same way that random forest tends to, where you tie together multiple models that may perform poorly individually, but together they do fairly well. Nope. A somewhat useful analogy might actually be like this picture. So let's imagine you suck at golf like I do, and you can't possibly hit a hole in one to save your life. So instead, you make this one hit so you make this one hit and it lands there. And so as it lands, actually, can you guys see my mouse or no? Because if you can't, this might be a little hard. Okay, sweet. So it lands here, and then now you're going to make a smaller change by jumping over here. And so in this case, this would be one decision tree in the case of random forest. This would be another decision tree. This would be another and another for 3 and another for 4. And so with gradient boosting, you're not quite using trees, but you're using something very similar. And so it's the same idea though, where you have this one major, let's call it a gradient boost, even though it's not actually what it's called. I forget the name for the life of me right now. But you have this, and then you have another one which is inherently weaker, but it still moves you a bit closer, which is where this like F1 gets at. But now F2 has you overshooting, but then F3 is able to do a little course correction, and then F4 does the final bit of course correction needed to actually get the ball into the hole, I guess. And so that's part of the power of gradient boosting. The other difference between gradient boosting and decision trees, because what you'll notice is decision trees, we got 82.75% accuracy, whereas with XGBoost, which is a gradient boosting library, we got 87.8. And so that I think actually beats out logistic regression. Yeah, by a bit. So part of that is because of the way in which gradient boosting works. So gradient boosting doesn't work on the concept of information gain. What it instead does is it tries to quantify it quantifies the distance between the prediction and what the actual value is. And then there's some learning rate. There's this idea of a learning rate. So the idea with the point of a learning rate is to prevent you from overshooting your goal too much to the point where you completely miss it and you can't get back. And so if memory serves, gradient boosting has a learning rate, which you can either manually set or just leave it as whatever the default is. But the point is that with that learning rate, you can then begin to integrate that change that you need to be able to get to your actual end result, but you integrate it in smaller steps rather than just like giving you the direct distance. And part of that is to allow you to build a model which tends to generalize better, because that's one of the things that you'll actually that you may have noticed is that just because the model does phenomenally well on, just because the model does phenomenally well on the training data. So here, I'll actually show you. So we have XGBoost. So what you'll see, so what this is showing you is when we actually run XGBoost or gradient boost, when we run gradient boosting on our training data, what we're seeing is 93.7% accuracy on the training data, which means that it correctly labels about 94% of all the data that it has and all the data that it's been trained on. And so it's good to see that it's not quite at 100%, because one of the like really big red flags with having it set to 100% is then you've probably overfit your train. You've run into this idea of overfitting. And so the problem with overfitting is normally you have to balance, like with supervised learning, you have to balance generalization and accuracy. And so if you are highly accurate to your training data, odds are you're going to struggle with generalizing to new data you've never seen before. And so that's something to be balanced. It's in the same way that like precision and recall, you're trying to push both up, but they tend to work against each other. And so that's something to balance. And while I didn't report it for all of them, like I could probably do that for like logistic regression. Yeah, so logistic regression does better on the training data than XGBoost. No. And then decision trees absolutely nail it when it comes to the training data, but then they suck otherwise. And then I think it was forest. Yeah. So if I run it, it'll take a little while on the random forests, but random forests also absolutely nail it, which is one of those ideas. So like random forests will tend to do fairly well from what I recall. No, what? Oh. Yeah, so random forest will tend to do fairly well, if memory serves, when you're dealing with your training data, because that's part of what makes random forest good, is they figure out the best way to split your training data. And obviously, that obviously means an assumption is that your testing data is going to look very, very similar to your training data, which typically, like if you have a good test train set, it should, but in the real world, it probably doesn't. So interestingly, naive Bayes hits 87.87, and oh no, never mind. I thought it was a lot closer for your testing accuracy. But yeah, so hopefully that was at least illuminating, if not enticing. I'm essentially done as far as I can tell. And at this point, I'm going to see if I can save this so it publishes. And yeah, so if anyone has questions of any kind, or like, I guess, because I had other slides that we could go through if you want. Actually, hold on, sorry. So there's one more slide to show. Yeah, if you can go to this link and drop some feedback of like, hey, John sucks at doing workshops, or something a little more constructive than that, that'd be great. And yeah, it's completely anonymous, so I'm not going to know who you are, so you should be fine. But yeah, so I don't know if anyone wants to, because the other slides that I have are mostly like, how do you talk to research faculty? How do you get into research? How do you find researchers and stuff? I wasn't sure if anybody wanted to talk about that. That was kind of what we were talking about during the break, but yeah. Wait, what? What? I'm not so, what? No. Okay. Here, hold on. There you go. That's the link. All right, yeah. So links, I don't know exactly how this will work. I think I'll just like post the links in the ACM Discord, or ACM-W. But if you also like if you hop onto the AI ECF Discord and you ask about it, it's like I'll probably respond too. I'm more responsive there. But yeah. So in terms of answering Victor Huang, over like how do you talk to faculty? So you basically go to this page. So on the slide deck, it's slide 49. You basically go to this page and it's going to show you all of the faculty that do machine learning and AI research. So from there, you basically start looking at like, oh, well, what are their areas? So there are 4 labs that are listed there, although I think that's about to be 3, because Ken Stanley is no longer faculty at UCF. But point is that you essentially start looking at like, it's basically, you're going to go down a seemingly infinite, you're going to go down a seemingly infinite rabbit hole of like, not buzzwords, but like topics. So like NLP, you're going to probably want to learn about that. You're probably going to want to learn about evolutionary computation and the like. But generally, at least the faculty will tend to give you a list of words that you probably need to know. And they're not going to be like, here's a list of words, but rather, here's what my lab does, and it does this, that, and the other thing. And those things that you just saw that they do, that's what you need to look at, because you want to figure out like, does this seem interesting to me? And then when it comes to emailing them, you'll email the faculty directly. When it comes to emailing them, don't do something like this. Like it's extremely vague, and this gets back at like what I think I had said, but I think others had also said as well on Monday, of like, that's a really vague statement. You certainly don't need to talk about this. Like, sure, Chloe, but also like, you don't, like, that's not what you say to like faculty. You're not like, hey, I think AI is dope, I want to work in your lab. Like, they'll basically respond like, cool story, bro, what do you want? And so yeah, right. So something like this is also like, you definitely don't need that. That's almost like, depending on how that actually turns out, that's almost like a PhD. But if you say something along the lines of like, here are my interests, like I'm interested in computer vision, maybe like this specific thing, if you want to be that specific, and I'm interested in reinforcement learning, it's like, that's perfectly fine. You've given them at least a way of narrowing things, and you've also demonstrated like, hey, I've looked into your stuff, and I have at least a rudimentary understanding of what these things are. And so, like I had said before, and like we had said on Monday, you don't need to have a thorough understanding of what they do. You just need to know, like, you just need to have like even the vaguest of ideas. If you go to like Dr. Shaw, for instance, he's going to give you an assignment. He's like, you've got a week to do it. Come back in a week. If you don't know what you're doing, it might take you the entire week. If you know what you're doing, the assignment will probably take you about 6 hours. That's not to say you should feel bad because it took you a week, but rather, he gives you a week for a reason. Take advantage of it. Yeah, and then so like here, so like hopping back. So when you come here, like if you click on Faye, for instance, when you click on Faye, so it'll actually show on her page, here are her research interests. And then, so that's something that's actually fairly new. They didn't have that when I started doing research. But you click, so like it'll show you what the keywords are at least, and then you can start looking into keywords. Another thing too is you want to look at their publication list, and you want to start looking through some of their publications. And at worst, so at worst, what you would want to do is find some look at their top 5, let's say, and in their top 5, then go out and actually read the abstract, and then, because the abstract is supposed to be a somewhat decent summary of the paper, and if it seems interesting, stick to it. And if you want to like learn more about how to read papers, I highly recommend coming to discussions, or at least like talking to people who tend to run discussions. There's too much to actually like break down for that right now. But yeah, and then so the other thing too is like I also kind of break it down in the deck. So you should be able to do that too, of just like reading through it. Yeah, and then you essentially just like repeat until you find faculty that are interesting. It's honestly like it's a brute force search, but I would argue it's worth it, but that's just because I find research interesting. So yeah, I think that's a long-winded way of saying if you're interested in doing undergrad research in AI or anything related to AI, yeah, you need to read papers and you're going to email the faculty directly. It's not as if you're going to go and like email Charlize and be like, hey, I'm interested in research. Who do I talk to? She's basically going to tell you everything I just did of just like go read the research pages for the faculty. I've done what I can to aggregate links, but I have not kept it like up to date. And I gave this in January. So point is that they might have changed some stuff. I don't know. But yeah, so I'll definitely be posting the slide deck though.